Hi all. So today we'll be seeing a demo on the pre-processing techniques that we apply on a text. That is, given a particular step, so what are the pre-processing methods or steps that can be applied onto it before feeding it as an input to a classifier or a machine learning model. Now, the common techniques that we apply are tokenization, lower casing, stop words removal, stemming, or lemmatization. Now we'll see each one of them in detail. So I'll be showing a demo of doing how we'll be doing these techniques. So here I have a Python program illustrating each of these techniques. Now at first what I have to do is I have to import nltk. Now what is nltk? It is nothing but natural language token kit. It is, as you know, it is a platform for building Python programs to work with natural language data or human language data. And this nltk has lot many text processing libraries, and using which we can do classification, then stemming, pre-processing, whatever techniques. It has got lot many libraries for processing the input data. Now we'll see each one in detail. Now at first I've taken a sentence. This sentence is nothing but the input. So this is a raw input that I give you, that is, it is named sentence, and it is a it is a sentence, and you can see the sentence over here also. Now this is the original input. Now what are the different pre-processing steps that you can apply on this particular input? So now first one is you have to change it to lowercase. So as you can see, once you run this one, you can see that the sentence is like, he determined to drop his litigation with monastery and so on. So here he is starting with capital letter. So what is done in lowercase is that we'll be converting the entire text to a single case, that is to lowercase. So that is nothing to add some to make it common, that is each and every word will be in a lowercase after that. So for that you will be converting into lowercase. So that itself is a pre-processing technique, that is lowercase. Now once you have converted all the words or the entire input text into lowercase, the next step is tokenization. So what is tokenization? It is nothing. The input is being broken, or it is being split into different tokens. Tokens, in the sense, you can think it as words. Now what does a tokenizer do? It has to divide the given input into different words. So obviously you should have some separator. Here it is a white space character, based on which it will be dividing the input text into tokens. So it is very evident that this particular sentence, this lengthy sentence, will be tokenized into he determined to drop his, and etc. So that is how it is tokenized. Now the next step is known as stop word removal. So before going into removal, you have to know what is a stop word. So stop word is, it is a word that does not add much meaning to a sentence. So we are trying to process the text in such a way that the meaning of the text should not be altered. That is, it should convey the original meaning, okay, even after doing the pre-processing. So there are some words which do not add any meaning or little meaning to the original text. For example, a, and, the, but, how, etc. These are all words that we commonly use in our input text, which does not convey any meaning to the original text. So even if you remove those words also, the meaning is not altered. So why is it necessary to remove these stop words? So we can think of our corpus or the input text as having in a common corpus itself. You take in a data set or something having textual information, it will have more than 25,000 rows and rows. So it will have many number of stop words also. So it will take many time to process or execute such data as well. So as to minimize the execution, the time, or to reduce the time, we can get rid of all such stop words also. So in NLTK itself, we have a NLTK offers libraries for it has a set of stop words defined for each and every language. So suppose we are having English as the root language, and so it has defined as many stop words for English. So we'll be cross checking our given the raw, that is the input that we are giving, that we have with the stop words that are available with NLTK. We'll be comparing all those things, and those stop words that we find matching will be thrown out of your input data, and we'll get a pre-processed or a new data, input data, that will be free from stop words. So now we'll see how that is done. So again, as I said, NLTK, it is supporting the stop words also. So we'll be downloading the stop words that are available with English language, and we have specified the language as English. And now we'll be removing all such stop words from the original text, and we get clean tokens. So tokens is already that is available, that is with stop words, and once you remove that, you get clean tokens. So now we'll see how what will be the output of such thing. Output will be, so here I had he determined to draw, these were the tokens. So once I remove the stop word, you can see that he is not there, he is removed, he is a stop word, he is a stop word, 2 is a stop word, then his is a stop word, and so on. So we'll accordingly we can reduce the number of words also. So that is what is known as stop words. So first step we did tokenize lowercasing, then we did tokenization, and then we did stop word removal. Now another topic that you would have encountered while studying this NLP is that POS tag. POS tagging means part of speech tagging. That is, it is used to tag the parts of speech, like that is, again I will show it with an example. So again, clean tokens are nothing but that is the input data that is free from stop words, and then you'll perform POS tagging. Now, so what is the output? How will be the output? The output will be like determined. So this determined raw, these are all our words that are free from stop word. So now what happens when we apply POS tagging onto it? So we'll have some phrases like VB and NN, then FW, JJ, and so on. So what does it mean? So it is some sample example. NN means it is a singular noun, and then FW means it is a foreign word, and JJ means it is an adjective, and NNS means it is a noun, which is a plural, and so on. So that is what is known as parts of speech tagging. That is, each token that you get after removing the stop words, the token that you get, you will be finding out, or you will be appending what is the actually the part of speech, whether it is a noun or it's an adjective or whatever it is. So that is also, that can also be done. So that is known as POS tagging. Now the next step is stemming. Now what is stemming? What is the use of stemming? So this stemming as well as lemmatization is otherwise known as text normalization techniques. Text normalization can be of two types, stemming as well as lemmatization. So what is actually done in stemming? Stemming is actually cutting the suffix from a word. That is, it will be cutting the word either from the beginning or from the end of the word, and the resulting word need not be meaningful also. So what is the use of this stemming? What is actually done, or what is the use of this stemming? So stemming, for example, if you have three words like in your corpus or in your input text, you have words like studying, studies, study, and so studies, and you have so many words. So these are all having the common prefix like study. So what is actually done is that after performing stemming, studying, studies, study, everything will be converted to a single text, that is study, because it doesn't have any change in its meaning. Even if it is studying or studies or studied, so everything is related to study. So you will be converting all such related terms into a single term, study. So that is what is known as stemming. So now we'll see how stemming is done. Again, you have in NLTK, we have a here we have a function that is known as photostemmer, using which a photostemmer, which is obviously a function or algorithm that can perform this stemming. So here also you can see that in nltk you are importing that particular function and it is called over here. So what is actually happening is that you'll be stemming all those similar words, because such words will be either taking some words from the beginning or end, and will be converting them to a common word. That's a more general option. As you can see over here also the example, like here and all claims and all, it is being converted to claim. Then wood cutting, it is converted to wood cut. Rights into right, ready, and everything like that. So you can get something, some words look the same after stem. Now a similar method, a similar one, that is yet another text normalization technique, that is known as lemmatization. So this lemmatization and stemming will be using interchangingly. You will be using stemming as or lemmatization. Anyone will be using. Now, what is the fundamental difference between these two? Lemmatization means it is more powerful than stemming, in the sense that it considers a morphological analysis of the words also. That is, the proper form will be looked up in a dictionary. That is, it is more related to the morphology of a word also. So it is found to be more powerful than stem. So here again, for us lemmatization also, we have a module or an algorithm supported by nltk, that is known as word-net lematizer. And similarly it will be once you feed the input, that is after removing stopper, that particular input is given to this lematizer, it will be lemmatizing. So now when you see the output, you can say it in the output is like this is the output. So the difference is that here determine in this case, just a second. So here in stemming you have determined the IE is missing. So when we consider the morphological point of view, it is determined. Then a little bit different, like many words like woodcut and woodcutting, then fishery. This is not like morphologically it is not correct. So it is converted to fishery, and likewise ready, REEDI, and that is converted to ready. So that is a proper form will be looked up in a dictionary. That is what is known as lemmatization, and found to be more powerful than stem nodes. Now what is the next step? So these are all the common techniques that we, or the common steps that we come across in text pre-processing. That is, as I already said, the first one is tokenization, and then lowercasing, or the otherwise lowercase, and then you tokenize. That is, first you will convert everything into lowercase, and then we tokenize it. That is, you divide them into different words or individual words, and then we do stop word removal. It is already have the collection of stop words that are available in English, and comparing it with the original text, we will be removing all stop words, since they don't imply any, they don't signify, that is, they don't give any meaning to or alter the meaning of your text. And then you perform stemming or lemmatization according to the application that you are doing. You'll do either stemming or lemmatization. So now that is done. So after doing all these process, you can say that your data is pre-processed, and it is pre-processed. So now, is it ready to be given to a model as an input? No. So model is obviously a machine learning model. So before giving it as an input, so this input is like the input is, it is a categorical data, it is a raw meaningful data, it is a categorical data. So the machine does not know what is this particular data. So what has to be done is that we have to do some sort of encoding. This data has to be encoded into another form so that the machine can understand it. So the main encoding methods that are commonly used encoding methods are one-hot encoding method, and we make use of word embeddings also accordingly. Now, so here I will show this one hot how is it encoding is done. So that also I will be showing you today. That is here. So this is after lemmatization, and then this is the, so actually what I have taken is I have taken this that is the input, that is lemma word is the it is the string that I get after performing lemmatization. That is morphologically my words are correct, and then that is stored in the variable lemma word. And so that is my vocabulary, that is I have such that much words in me. So if you see that after lemmatization, I have printed the length of my output, and that is 23, which means that determine, drop, this, etc. It is having 23 words. It is having 23 words. So this is my vocabulary. So my vocabulary is having, we'll see one hot vector encodings. So here we have, so already, as already said, we have taken the input of the output of lemmatization as the input to our hot vector encoding method. So the lemmatization word is having a length of 23, which means it is having 23 words. So at first step, what is done is we have to create a vocabulary. Vocabulary means a set of words. So actually my set of words, I am having 23 set of words. So what I do is I build a vocabulary, that is a random listing of the above set 23 words. So here it is determine, drop, litigation, monastery, etc. And what I do is I make a random listing using the function set. So set of lemma word means this particular list is taken, and a randomized listing will be generated. So that is valuable, drop, monastery, leak, claim, indeed, etc. Now what is done is, in hot vector encoding, what is actually done is that the categorical data will be taken as input, and that is converted to an integer, and with that particular integer is again converted to a binary vector. So it is happening in that way. That is, first of all you have some categorical data, that is that may be a textual data or whatever it is, and then that is converted to an integer data, and then that integer data is converted to a binary data. So one hot vector representation is an encoding scheme which will convert the categorical data into a binary data. In between it is actually transformed to an integer also. So how is that actually done? So as of now what we have done is we have made a random listing of the lemmatized words which we call the vocabulary. So we have vocabulary with us, and now each individual word is converted to an integer. So what is that? How is that converted to an integer? So actually the sequence is determine, drop, litigation, monastery, etc. So what we do is we'll first check with determine, and we'll check for the location of determine in this particular vocabulary. This is our vocabulary. So in vocabulary it is coming in the 9th position, that is 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Again we'll check the next word, that is drop, and so here it is coming as the second word, so it will be 0 and 1, that is it is coming in the location 1. Now again we'll check with the third word, that is litigation. So in litigation it is actually coming over here in this particular location, that is the 12th location, that is starting from 0, it is happening as the 13th word. So that is how, so what we are doing is we'll be converting each individual word in the that is a pre-processed word that is mapped to an integer value like 9, 1, 12 and so on. So once we get this mapping, this particular mapping is again converted to a matrix, and this matrix will be obviously a binary matrix. So actually how will you generate this particular matrix? So actually the first value is 9. So 9 means which is similar to the word determine. So what is actually done is that the first row, all except the 9th value, the 9th location value, that is 0 to 9th value, all others will be 0. Again we check for the second word, that is drop, which is having an integer, which is mapped with an integer value 1 according to the vocabulary, and so 1 means it is in the location 1. So here the second row, first value will be 0 and the second one will be 1, and all the rest of the values will be 0. Similarly the third word, that is litigation. Litigation is here, it is in a location 12, that is 0 to 12, that is 13th location. So similarly the third value in the 12th location, that is 0 to 12th location, or the 13th location, you will have a 1, and the rest of the values will be 0. So correspondingly these 23 values will be mapped mapped into such a binary matrix. So this is actually what is happening in one hot vector encoding. So you can see that in every row we'll have a single one, and in every column as also we'll have a single one corresponding to that particular one, and all the other values will be 0. So it is a binary matrix. Now, what is the drawback of this one hot vector representation? So in this example, we have taken a single string or a single text as an input. So here I have taken a single, I call it a sentence, and that is a single text. I take it as a single one. So here it is having more than 23 words, and after stop word removal and everything, I reduced this number of words to 23. Here I have reduced the number of words to 23. Now, so here the length of the text is actually 23. What if I am giving another text? Suppose that I am having my first text is having a length 23. After pre-processing, it is reduced to a length 23. The second sentence, it is after stop pre-processing, it is reduced to 20. Now third sentence having a length of something and then reduced to 9, and the fourth sentence having a different length, say 12. So what if the length of the sentence are varying, like 23, 20, 9, 12, and 10 and 12 and so on? So it will be very difficult to encode them if the inputs are of varying. So in this case it is not a problem, since we took a single text which is of length after pre-processing, that is 23. So what if we have many such sentences, each of varying length? So in such a case we have to make all these two, or we have to arrive into a common length. So in that type of encoding is known as embedding. In embedding, what we do is we'll try to make all inputs, we'll make them the same size. So we'll set some size, like length will be set to some 30. So in that 30, what will be actually happening? The maximum size that is permitted for an input is 30. So if the input is 30, then it is okay. After pre-processing, the input is 30, it is okay. That works fine. And if it is 23, it is not equal to 30, it is less than 30. So what we have to do is we have to add extra values to it, or that is what is known as padding. So we add some extra zeros to it, or you pad zeros to them so as to make their length to 30. So what we have to do is we have to add 7 more zeros to make it 30. And if it is 9, the length after pre-processing, if the text length is only equal to 9, you have to make it up to 30. So likewise, what we are doing is we'll be making all the inputs to, they will do it in such a way that after this embedding, all the inputs will be of the same size. So as to make all inputs arrive into a common size, we make use of embedding, and that is known as word embedding. So here in this case, since we have taken a single sentence as our input, it doesn't we can't feel the difference. But if we go for more number of text, then we could feel the difference. So actually again this embedding, what we do is we'll pad some values. So this is what is known as padding, and pre means we'll be adding zeros as the prefix of the existing text, and the max length here it is set to 30. So what will happen if the length is set to 30, which means the maximum size that is permitted for an input is 30. So here you can say that the array will be having a value of length of 30. Here it was 23 because the length of the text was only, and the number of elements in this lemmatized words were only 23. So it depends on the input that you are taking. But here we have standardized, or we have made it common, the length of the input. So if it is 23, you will add 7 more. You will pad it with 7 more zeros. And if it is 20, you will pad it with 10 more zeros, and so on. So word embedding works fine even if the inputs are varying, and that creates a problem with one hot vector, because one hot vector means the matrix is completely dependent on the number of words in the pre-processed text. So as to make it uniform, we go for word embedding, where we'll fix a maximum size, and if the given input or the pre-processed input is the length is not equal to the maximum set size, then we'll pad it with more zeros. So the maximum size, everything is mentioned over here. So the length is 30, and what we do is we'll pad the sequence with we'll that is zeros will be added as a prefix, and this transformed is nothing but the one hot vector that we get from the previous code. That is, this is the transformed means the one hot vector, and that is actually given as input, and then we prefix it with zeros, as many zeros, so as to make it equal to the maximum.